positive semidefiniteness and eigenvalue approximation. This is joint work with Deanna Needell and my postdoc, William Swartworth. So let me start by defining the problem that we're going to study. So we're given a symmetric real-valued matrix A. Let's say it's D by D. So it has D eigenvalues. And the question we're going to ask is, how many linear measurements, I'll say what those could mean in a moment, of A do we need to distinguish between the following two cases? One is A is positive semi-definite. Okay, so all the eigenvalues are non-negative. And two, A has a sufficiently large negative eigenvalue. Those are the two cases you want to distinguish. Yeah, so PSD here is symmetric and all non-negative eigenvalues. What are some example situations where this problem might arise? So A could be the Hessian of a loss function f of a neural network evaluated at some, with some current assignment of weights, let's say x0. And in this case, this matrix A is not given explicitly. It's impractical or infeasible to write down the Hessian of a large neural network. And this is going to motivate us looking at this matrix A via these linear measurements. And we maybe want to distinguish between the cases that we're minimizing a loss function f. So is it minimized at the current set of weights? In that case, the Hessian would be PSD. Or is it not? Is there a steep descent direction at the current assignment of weights? So it has a large negative eigenvalue. And in this particular application, certain linear measurements are very natural. So one kind of linear measurement is a matrix vector product. Given a matrix A that we don't have explicitly, we can still query it through vectors V of our choice. So we get to see A times V. And in this particular example, it is possible to get Hessian vector products using automatic differentiation and other techniques. Another kind of linear measurement is a bilinear form query. I'll call it a vector matrix vector query, where you choose vectors U and V on the left and the right, and you observe U transpose AV. This is also well motivated for this particular neural network application, where this corresponds to a single second derivative, directional derivative calculation, and it can be approximated with a small number of function queries. So, this is the setting. These are examples that we're looking at. Also, linear measurements come up all the time in streaming and communication settings, as you know. They're useful because linear sketches are easy to update, and they're mergeable, and so on. OK, so let me formally define the epsilon LP tester problem that we'll look at. So given this matrix A implicitly, if A is PSD, we'd like to declare that it's PSD with some constant probability. And if A is epsilon far from PSD, what that's going to mean that its minimum eigenvalue is less than minus epsilon times some matrix norm of A. We have this gap depending on the norm so that it's scale invariant. Okay, and this matrix norm, I've written A sub p. This is the Shadden p norm. It's just the p norm of the eigenvalues of your matrix. Okay, so are you PSD or are you sufficiently far from it in Shadden p norm? And when p is 2, this is the Frobenius norm. So we ask ourselves, how many queries does a tester need in these various models? Matrix vector queries, where we just query with adaptively or non-adaptively with vectors V. Vector matrix vector queries, I said. We're going to focus on these two models, though you could also look at general linear measurements, where you just take the dot product of your matrix entry-wise with some other matrix M. As I said, we're going to consider both adaptive and non-adaptive testers. Adaptive testers are motivated from various optimization procedures that are often performing things like a power method or Krylov subspace iterations. Non-adaptive testers are motivated from streaming. And we aim to give tight query complexity bounds. Okay. So let's first look at matrix vector queries. And let's look at p equals 1, OK? And without loss of generality, we can assume that the one norm, it's just the sum of the absolute values of eigenvalues of your matrix, is 1. Okay, the whole problem is scale invariant. Okay, so how can we tell if A is PSD or it has an eigenvalue that's less than minus epsilon? And here's what we're going to do. We're going to use what's called the Krylov iteration to approximate the top eigenvalue, not of the original matrix A, but of an appropriately scaled and shifted matrix. Okay, so let me say what happens here. Here's your matrix A in pictures. Okay, so this is the spectrum. Here's 0, and A might have a lot of positive eigenvalues. In fact, it might be PSD. Or there might be this red negative eigenvalue. Okay, and we want to know if this exists or not. So how can we figure out if it exists? So we can look at minus A. That'll flip the spectrum around 0. So now it looks like this. We can then add a multiple of the identity. So I'm going to add lambda times the identity. That'll shift all the eigenvalues. And so now this new matrix has all positive eigenvalues. If I choose lambda appropriately, I'm going to choose lambda to be larger than the largest eigenvalue of A. The largest eigenvalue of A is at most 1, because the norm of A is 1. Now I have this new matrix, and my goal is to estimate the top eigenvalue of this matrix. So I want to estimate this top eigenvalue up to additive epsilon error here. That will tell me if this red dot existed or not. Now, as we said, lambda could be as large as 1. So what that means is that we actually have to estimate the top eigenvalue up to a multiplicative 1 plus or minus epsilon factor. Okay, in the worst case. And a good way to do this is with the Chebyshev trick. Okay, so you can estimate the top eigenvalue of a matrix with 1 over square root epsilon matrix vector queries. So let me just review that. So assume that you have a PSD matrix M. Then the idea is to choose a random vector V, maybe a Gaussian vector. Then just iteratively compute V, M times V, M squared times V, and so on, M to the K plus 1 times V. This is an adaptive algorithm. And once you have these matrix vector products, now you know how this, you can combine these matrix vector products to learn the any polynomial of the eigenvalues. So I take any polynomial of this matrix M. That just means I apply the polynomial on the eigenvalues, as long as the polynomial has degree at most k. Okay, so I learn P sub k of M times V. So an appropriate combination of these. And the nice fact here is that there exists a polynomial P of degree k, where k is square root lambda 1 times 1 over root epsilon times log 1 over delta, such that this polynomial, well, it's going to evaluate to 1 on the top eigenvalue. And it's going to evaluate to something really small in absolute value. So evaluate to at most delta if I move a little bit away from the top eigenvalue. Okay, if I move epsilon away. And so this polynomial is great. You can think of it as just retaining the top eigenvalue and zeroing out all the other eigenvalues. There's a logarithmic dependence on this delta. So if I look at this polynomial, then applying that to the matrix M and multiplying by V, this is going to align very well with the top eigenvalue of M. Okay, because this P of M, as we just said, is kind of like just the outer product of the top eigenvector with itself. And I take the dot product with V, and I get a vector which really looks like the top eigenvector. And so this Krylov space witnesses the largest eigenvalue to m, to within epsilon additive error, which is what we wanted. And so we can just compute these products and then maximize the quadratic form to compute the top eigenvector in the Krylov space, which we know. So we don't need to know this polynomial to figure out a good bound on the top eigenvalue. Okay, all we need to know is that this polynomial exists. Okay, because we can just optimize, choose the best vector in the Krylov space, the one that maximizes the dot product with m. And we already have all the Krylov, we have the Krylov space, we have all the matrix vector products we need. Okay, so this is very simple algorithms, and it gives 1 over root epsilon matrix vector products. Are there any questions about this? Okay. Do you think this is best possible?
No.
No. Okay. I'm hiding log factors. Yeah. Okay. Why do you say no? Or
Talk with the over other
okay. Okay. Well, what do you think we might be doing suboptimally? What was one of sort of the bottlenecks in this algorithm? Yeah.
It's like eigenvalue close to 1 is where you have this worst case guarantee, but that feels like you have some sort of trade-off in the structure. There's some of your eigenvalues has to be 1.
Yeah, that's exactly right. So we had to shift a lot, right? Potentially shift by 1 times the identity. So is there some way we could avoid shifting so much? And so the idea is, well, what if we could somehow first deflate, that is, zero out the largest few eigenvalues of this matrix, and then perform this process? So then we would have to shift less, because if these eigenvalues go away, repeating the same procedure where we negate and then shift, we see that we shift by less here. Okay, so maybe we can try to balance the number of matrix vector products we need to deflate together with this, this algorithm that we just presented. So the idea is, let's deflate the top t eigenvalues, where t is going to be chosen to be something like 1 over epsilon to the 1/3. And I'll say how to do this in a moment. Now, we know that the sum of absolute values of eigenvalues is 1. And so the new maximum eigenvalue after zeroing out the top t has to be at most 1 over t, which for this setting is epsilon to the 1/3. And now if we go through the same algorithm we just did on this deflated matrix, A with the top t eigenvalues removed, then we don't have to shift by as much. We only have to shift by epsilon to the 1/3 instead of potentially 1. And so now, if you look at it from a relative error standpoint, we only need to estimate the largest eigenvalue up to 1 plus or minus epsilon to the 2/3 multiplicative error. And now, using the Chebyshev trick on this matrix, we only need the square root of this, which is 1 over epsilon to the 1/3 queries. Okay. Now, I didn't say how to do the deflation yet. Deflation can be carried out explicitly via Cameron and Chris's algorithm analysis of subspace iteration. But in fact, Krylov just does this directly for us. We don't need to do this explicitly. So we can consider a polynomial which, instead of being degree 1 over epsilon to the 1/3, that was this q of x in the earlier algorithm description. There's this polynomial that if you unshift and go back to the original matrix, it's very large value at the negative eigenvalue and roughly 0 at all the positive eigenvalues. So that's that polynomial q. And what we can do is we can force it to be 0 at the top t eigenvalues. So that's how we do the deflation. We just multiply by x minus lambda 1, x minus lambda 2, and so on. And so we choose a number of values that we set to 0 to be the same as this original degree. So the overall degree just changes by a constant factor. We also normalize by a scalar here so that p of the negative eigenvalues still remains 1. And you can show that p evaluated at the smaller eigenvalues, at the positive eigenvalues, is still very small. Okay, so you have a low-degree polynomial in the Krylov space without having to explicitly do the deflation. Yeah?
You need estimates of lambda 1 and lambda t to do this, right?
No, so you don't actually need to know this polynomial. You just need to know that it exists. Okay, because in the end, what you're doing is you're going to build up this Krylov space by doing these adaptive matrix vector products. You have this Krylov space. And now you know there's some combination of the matrix vector products that you have that is, that realizes the polynomial applied to the matrix. And if you were able to choose that, that'd be great. It would give you, a vector that's very aligned with the negative eigenvector. You don't know what that polynomial is, but you have all these matrix vector products. So you can just choose the best one in the space that you have. So it's a nice, in the sense that you just need to know that this exists. Any other questions? Yeah.
I guess, can you also alternatively think of like a polynomial that kind of zeroes out the interval between 1 and like something close to epsilon in the real line?
So what you wouldn't be able to like zero out the interval, right?
But you could make it very small.
We don't need to do anything beyond these top eigenvalues.
I see. Okay.
Yeah. Okay.
Are there extremal results known about like the optimality, the degree of the polynomials?
I don't know in terms of like constant factors and logs. I don't know exactly what the lower bounds are. Maybe someone else knows. Anyone? Okay. No. Yeah. I think it's optimal up to higher order terms. Yeah. Any other questions? Okay. Yeah. So this is what the polynomial looks like, right? It zeroes these out, and it's very small on the positive eigenvalues, and it's very large at this negative eigenvalue. It exists. That's all we need to know. And now we can just minimize the quadratic form of A over the Krylov space, and we'll know that we'll get a negative value. And that's all we need as a proof that this matrix is not PSD. Okay. Yeah, so that's it. It gives 1 over epsilon to the 1/3 matrix vector products. It's kind of a weird bound. You can generalize it to arbitrary p norms. You get something like epsilon to the minus p over 2p plus 1. This bound goes to, it gets worse as p increases. It goes to 1 over root epsilon for large p. And essentially what that's saying is the deflation is not as effective, right? If p is infinity, then deflating the top few eigenvalues, well, you could still have another one of the same value. So this bound, it doesn't look very nice, but in fact, it's optimal. So using a lower bound technique of Braverman et al., we can show that these bounds are tight in this model. I'm not going to get too much into it, but they have a nice result that says if you have a Wishart matrix, so a Wishart has the form GG transpose, where G is Gaussian. It's a D by D matrix, and you want to estimate its smallest eigenvalue up to a constant factor, then you need D matrix vector queries. Okay, so the smallest eigenvalue is not very concentrated, unlike the top eigenvalue. And if you want to estimate it well, then you kind of need to read the whole matrix. And you can embed this problem into our problem by appropriate setting of parameters. Yeah.
Does it even for p equals infinity?
For p equals infinity,
Arbitrarily large p.
yeah, so
Non-constant p.
for non-constant p. I don't know what the dependence, if there's a dependence here on p or not. I'd have to check, yeah. But I mean, it gets arbitrarily close for constant p, yeah.
Thanks.
Yeah.
Just a small comment. I think in the p equals 1 setting, which is what you demonstrated.
Yes.
There's a very similar argument in the result of Spielman and Wu, which basically says in the graph setting, if you have such a sum on eigenvalues, conjugate gradient basically gets the one, like at least theoretically gets a cube root kappa convergence, which is the same proof.
Oh, okay. Does it generalize to?
I mean, the the construction of the polynomial is the same, that you
Okay.
have it exactly 0 at the top roots, and the lower one, and then now they're smaller by some norm there.
Okay. Okay. Yeah, we should talk more about that afterwards. Yeah. Okay. So that's one example of techniques here. Let me look now at bilinear sketches, so vector matrix vector queries. Let's again look at p equals 1. We want to test if we're PSD or far from this. A natural way of sketching is to compute GA-G transpose, where G is a Gaussian matrix, with hopefully a small number of rows. And so the number of vector matrix vector products here is 1 over epsilon squared if I have 1 over epsilon small dimension for G. If A is PSD, then GA-G transpose is also PSD. And if A is far from PSD, then actually using analysis of Andoni and Hui, if it's epsilon far, you can show that it won't be PSD. Okay, so you can just check if GA-G transpose is PSD or not. This has the nice property of being a one-sided tester, meaning that when the input is PSD, it always returns PSD. And this is also optimal. I won't say why. Okay, so that's for p equals 1. But what about p equals 2? And interestingly, there's a very different behavior here. So there's a strong lower bound here that no one-sided polynomial in 1 over epsilon L2 tester exists for vector matrix vector queries. In fact, you can show that you need epsilon to the -2 times d vector matrix vector queries. Okay, so it suddenly becomes polynomial in D once you look at norms p larger than 1. I'm not going to say what the lower bound is, but it's since there's a streaming crowd here, I want to say that it's related to frequency estimation arguments in data streams, which say that if you, it's well studied that you have a vector and you want to produce a sketch of it to approximate frequencies, values in that vector. And if you're required to always produce overestimates of these frequencies, then the problem actually becomes much harder. Okay, so if you're familiar with things like count sketch, these give you two-sided estimates. Sometimes they're less than the actual value, sometimes they're larger. And that's actually essential. If you require one-sided, then the space complexity grows a lot. And actually, that phenomenon is related to what's happening here. OK, but that's just for one-sided testers. Maybe we can allow error, two-sided error. So let's try to diagnose the problem. What's happening here? Well, what is the natural algorithm? We can take the algorithm of Andoni and Hui, and it's computing GA-G transpose, and look at its eigenvalues. It seems like a natural thing to do. The problem is that the eigenvalues of GA-G transpose are going to concentrate around the trace of the matrix A, which can be very large. It can be as large as square root d times the Frobenius norm. So unlike the simple tester for p equals 1, where you just check, is there a negative eigenvalue in GA-G transpose, you're unlikely to observe any negative eigenvalues in the case where you're epsilon far in the 2 norm. What's going to happen is you're going to have a bunch of eigenvalues that concentrate around the trace of A. And then maybe if you had a negative eigenvalue in the original matrix, well, maybe it'll be a little bit less than the trace of A. But it's still going to be very positive. OK, so the key idea that we use is, well, maybe we can look at the positions of the eigenvalues relative to the trace of A. OK, and we're going to reject if we're going to say we're going to say A is not PSD if GA-G transpose has a suspiciously small looking eigenvalue. OK, so formally, what does this mean? Let me just say roughly how the analysis goes. So what we can show is that if the original matrix A has a negative eigenvalue smaller than -epsilon, then with good probability, the minimum eigenvalue of GAG transpose is a little bit away from the trace of A. Okay, so it's the trace of A minus at least epsilon times K, where K is the number of rows in your Gaussian matrix. Okay, so it's it's a little bit negative. It's a little bit far away. Let me not say much about the proof, but the idea is just to choose the vector closest in the image of G to the negative eigenvector, and you can show you gain this little bit amount. Okay, I'm not going to say more. On the other hand, what you can show is that if A is PSD, then actually all the eigenvalues of GAG transpose are within additive root K from the trace. Okay, and this uses a net argument. So in fact, we only need the lower bound here because we're going to try to distinguish. We're going to look at the minimum eigenvalue of the sketch as our distinguisher. We only need the lower bound, and so the idea is to look at a net of all vectors V in this k-dimensional space, and use a Hansen-Wright inequality to it's concentrated, and with the appropriate inequality, you can lower bound how much you deviate from the expectation. And that's it. So the idea is if you're epsilon far from PSD, you can show the minimum eigenvalue is a little bit far away from the trace of A. On the other hand, if you're PSD, the minimum eigenvalue is somewhat close to the trace of A. You then choose your number K of measurements to separate these two cases. And if you just solve, you see that you need your Gaussian matrix to have 1 over epsilon squared small dimension. Yeah, so the idea is just compute the minimum eigenvalue of the sketch. In parallel, you need to estimate the trace of A. That can be done easily with known algorithms. And then you just check if this minimum eigenvalue, how close it is to the trace, to your estimate of the trace. Okay. And that's 1 over epsilon to the 4th vector matrix vector queries, because it's GAG transpose, and that actually turns out to be optimal as well. Any questions about this algorithm? Yeah.
Yeah. So when you talk about concentration around the trace, is there an assumption here that dimensionality is just much larger than K, and that's why this is the case? Because if they were proportional, then it wouldn't concentrate, right?
Yeah, I'm thinking of K as being something that's much smaller than the matrix dimension. You're trying to sketch and reduce it. Yeah. Other questions? Okay. Don't have much time left, so let me just give you a flavor of other techniques in this area very quickly. We saw that for L1 testing, there's this bilinear sketch GAG transpose that has 1 over epsilon squared vector matrix vector measurements. That was Andoni-Hui's algorithm. You could ask yourself, can you improve this with adaptivity? I said it was tight if it's non-adaptive. And in fact, you can get 1 over epsilon measurements with adaptivity. And to me, it's kind of surprising because I haven't seen algorithms of the form of vector matrix vector queries that exploit adaptivity. Usually it's like these Krylov methods, matrix times vector, and so on. But so how do we do this? What's the rough idea? The idea is, well, we're trying to minimize this quadratic form x transpose ax, right? We're trying to see if this value ever gets negative. That means it's not PSD. And we're going to run a kind of cheap gradient descent here, which uses very few vector matrix vector queries. And here's the idea. We're going to initialize a vector to be Gaussian. And we're just going to do the following iteration. The new iterate at time k plus 1 is the old iterate minus an unbiased estimate of the gradient. A nice thing about this unbiased estimate is there's only one vector matrix vector query here. So you choose a Gaussian at the case step, and you look at Gaussian transpose times matrix times your previous iterate. That's your single vector matrix vector query. And you multiply that by the Gaussian you chose. Okay, so there's only one query to A here. It's an unbiased estimate of the gradient because if you look at G transpose, the expectation is the identity. And what you can show is this algorithm, if you run it for 1/epsilon iterations, with high probability, you will actually choose an iterate, find an iterate which shows the quadratic form is actually negative. So that's one way of using adaptivity here. Any questions about this? OK. And finally, let me just say one more thing is that this study into testing of PSD matrices led to new algorithms for spectrum estimation, so approximating all the eigenvalues of a matrix. So here's the problem statement. Assume you have a symmetric D by D matrix A, not necessarily PSD. Your goal is to construct a sketch of A to recover the eigenvalues. And what we want to do is we want to estimate every original eigenvalue of A up to additive epsilon times the Frobenius norm of A. So this is going to be good for eigenvalues that are large. For very small eigenvalues, the estimates are not going to be interesting. It'll just be 0. But that is for good reason. Okay, you can't actually estimate very small eigenvalues well with small sketching dimension. So the question is, how small can a sketch be? Previous work that I mentioned shows you can do this with 1/epsilon to the 6th vector matrix vector queries. It's this G transpose sketch with 1/epsilon cubed small dimension on both sides. But it has some drawbacks in the sense that the sketch can't actually recover the signs of the eigenvalues. It loses that information inherently. So what we show is that by taking this approach for testing, but our analysis of G transpose, well, what we can do is subtract off the trace. That's the sort of most concise description. So we look at G transpose, the same sketch, and the expected value of its trace is the original trace, but now it only has k dimensions. So the eigenvalues average at 1/k times the trace of A instead of 1/d times the trace of A. And we correct for this by subtracting off 1/k times the trace of A times the identity. So we have our sketch, and we subtract off a multiple of the identity to try to correct for this. And so this is the whole algorithm, and I'll just end with this. It's a very simple algorithm for estimating eigenvalues. Choose a Gaussian matrix G with roughly 1/epsilon squared rows. Compute the sketch G transpose, really small, 1/epsilon squared by 1/epsilon squared. And just output the eigenvalues of the sketch minus this multiple of the identity, trace of A over k. Compute those eigenvalues. You're only going to get k of them. And you want to estimate d eigenvalues for the original matrix. For all the remaining eigenvalues, just estimate them with 0. This algorithm works. It's simple, it's easy to implement, and it gives optimal sketching dimension. And let me just conclude then. So we gave tight bounds for PSD testing and spectrum estimation under natural measurement models. There are lots of nice questions here. Our proof for spectrum estimation requires the sketching matrices to be Gaussian. It uses Gaussianity in several places, uses rotational invariance to imply independence of certain quantities. We don't know if you can use sparse sketching matrices that would speed it up. We don't know if adaptivity helps for spectrum estimation in terms of vector matrix vector queries. So we got a tight 1/epsilon to the 4th bound. Maybe you can do better with adaptivity. And there are also other models for PSD testing. Instead of just having one large negative eigenvalue, maybe you have a lot of negative eigenvalue mass, but no particularly large one. What can you do in that setting? So that's all. Thank you.
We're running a bit over time, so maybe one question before our next speaker. Anyone?